Okay, so what are these two complementary amine synthesis methods? We just showed them, and let's look at them again. And it's a great way to snap um, um, pieces together to create amines. Very, very synthetically useful reactions. Reductive amination. So you make an imine and you reduce it, and the reducing agent's sort of a special reducing agent. NaCnBH3. There's ways to use like NaBH4 also, but NaCnBH3 is very suitable for this reaction because it only makes imines. It doesn't really, it only really reduces imines. Okay, here's an example. So amine, aldehyde, and so these two react. Sometimes it's low pH, so we could also call it H plus cat, right? A little bit of acid catalysis creates the imine intermediate, and then it's reduced by H minus. So H minus attacks, and then you make an N minus, then the N minus grabs a proton from methanol or whatever. And this is a wonderful way to make amines, right? You can take almost any left piece and almost any right piece, snap them together in the presence of NaCnBH3, and you just created a new amine. So the other thing you can do is synthesize amides and then reduce them. So make an amide, reduce it. So all you got to do is, review how to make amides. Amides are very easy to make. There's a million ways to make amides, and then you can reduce them, right? Here's an example. So take a carboxylic acid, make an acid chloride with SOCl2. So it creates the acid chloride, and then the amine reacts with the acid chloride, kicks off the chloride, makes an amide. Make an amide and reduce it. And then you treat this. You need a strong reducing agent, but it just wipes away the C double bond O. Wipes it away, and now you're left with, in this case, a secondary amine. Okay? So these can be applied to make almost any amine in the universe. Okay? misc alcohol reactions. How to convert a alcohol to a good leaving group. So this is kind of organic 1 material, but it's a general reaction, and you gotta at least know what the reagents are. This just kind of shows a couple of the examples. SOCl2 converts alcohols to chlorides, and if it's on a secondary carbon, it actually inverts it to, because it is an SN2 reaction. Oxygen attacks sulfur, kicks off a chlorine, and then chlorine comes back and kicks that off, right? So if oxygen attacks, that makes this whole thing a good leaving group, and then chloride attacks and kicks that off. So that's why it inverts. And then if you throw in another nucleophile, it does a double inversion. It inverts once, it inverts twice, and then you have this. PBr3 does the same thing. And so oxygen attacks phosphorus, kicks off Br, makes it a good leaving group. Br attacks, kicks off that, and then it does a double inversion. So, and then your stereochemistry in the end stays the same. Okay, but what if you want to do a single inversion? So then you can use a different reagent called Taz chloride or Tazol chloride. Then oxygen attacks Tazol, kicks off chloride, and it makes this as a leaving group, and then your nucleophile attacks, kicks that off, and then it ultimately does a single inversion. So yeah, these are just a couple of ways like that you might turn alcohol, which is a bad leaving group, maybe into a good leaving group, and then kick it off. Now this whole chirality and stereochemistry thing only applies if it's secondary. If you have a primary alcohol, there's none of this. It's just, there's no stereochemistry, right? So, but yeah, for the most part, you guys know about like PBr3 makes a bromide, and you can do some reactions with that. Alright. Alright, so let's see if I can move my little thing up here. Alright. Alkenes, this is technically chapter 12 or organic 1. We've reviewed a couple of these reactions, but it's really not a big focus of organic 2. So reviewing all the reagents, I would say, should be a low priority thing. And remember also that this is open note for you. So maybe good for you to write down these reagents just for your own use, and GREs and MCATs and stuff. Hydroboration oxidation is BH3, which is Markovnikov. This is, oh wait, I got it backwards. Nope. Markovnikov is mercury acetate, HgOAc2. HgOAc2. This is hydroboration oxidation, anti-Markovnikov. This is BH3. How do you go from alkene to alkane? You should all know that one. These you might forget. This you should know. This is H2 palladium, right? The dihydroxylation is osmium tetroxide, OSO4. And also to a bromide, Markovnikov bromide is HBr. Anti-Markovnikov bromination. This is HBr peroxides. So it's HBr peroxides. It's a radical reaction. This is a carbocation reaction, and that's why the Br goes to the stabilized carbocation position. This is a radical reaction, totally different mechanism, and it puts the Br at the end. This one you should know, not necessarily the mechanism, but you should know that alkenes react with MCPBA to make epoxides, and then if it's an acidic nucleophile, then it's an SN1 opening. Well, it's actually if it's tertiary, if it's a tertiary epoxide, then it's SN1, and then the X group goes to the tertiary position. This situation is secondary, so X would just open up from the least hindered side. That is technically chapter 9 stuff. I wouldn't worry about it. You do know this. We have exercised though that basic nucleophiles like Grignards attack from the least hindered side, and the nucleophile goes there on the right. And then Br2 in chapter 9, Br2 water, chapter 9, ozonolysis is kind of chapter 9. We did mention a little bit in chapter 12, but so be aware of this one, but don't worry about all the mechanism and everything. It's O3, ozone, and it's zinc acetic acid, ZnHOAc or something. Okay. Cool. Alkynes. This is definitely an organic 2 this is organic 2 stuff, so definitely more reasonable for something you might see on the final, cumulative final. Yeah, so what are the alkyne reactions? Well, and the cool thing, and the reason, part of the reason we reviewed chapter 12 just a second ago, alkene reactions, is because the alkyne reactions are similar, right? So with the alkyne, you can go to the Markovnikov one and ketone, and that's mercury, right? Mercury, it's not mercury acetate, it's not HgOAc2, it's actually mercury sulfate. So with alkynes, it's a different mercury. It's HgSO4. And then there were a couple steps, and it actually made an enol. It actually first created an enol, and then the enol tautomerized to the ketone. And that, you didn't actually learn that till way later, right? When you learned this, you didn't know about enols and enolates and all that stuff. So you didn't really understand the full mechanism. And there's no stars here. The mechanisms aren't really a big deal for the final, but understanding the reactions and maybe the reagents might be useful. And then so there's a boron version of the alkyne for the alkynes that gives you an aldehyde. So it's a BCY2, right? Or it's HbCY2. So it's dicyclohexyl borane, and the cyclohexyls, the CY. I can't really draw out the mechanism, and it's not really that big of a deal. But the cyclohexyls basically want to be away from all of this stuff, and that's why it's a concerted reaction mechanism, and the cyclohexyls want to be far, far, far away from everything. And that is ultimately why you get anti-Markovnikov. The oxygen goes on the far side. It's all because the cyclohexyls want to be away, and the cyclohexyls are attached to the boron, and then the conversion of the boron to the oxygen, we never really covered that anyway. This is easy though. This is just to rip off the proton, attack an alkyl halide. And these are also easy, right? Rip off the proton, attack a, what's that, a aldehyde, right? Rip off the proton, attack a what? Epoxide. This, and then we can do these kind of bromination things, hydrobrominations, partial hydrobromination, HBr, it's a carbocation type. No, I'm sorry, that's anti-Markovnikov. It's not HBr, it's anti-Markovnikov, so it's HBr plus something, right? HBr plus, and it's a radical reaction, HBr plus peroxides. HBr peroxides gives you anti-Markovnikov, just like it did on chapter 12, the alkenes. And then this is HBr, no peroxides. So this is Markovnikov. Okay, Markovnikov, HBr, anti-Markovnikov is HBr peroxides. And then we learned that alkynes can be reduced in a couple different manners. They can be completely reduced with H2 palladium. They can be partially reduced with is it sodium ammonia or lithium ammonia, NaNH3, not NaNH3 like a reagent, and that's impossible. You know about NaNH2, Na plus, NH2 minus, but when you say NaNH3, that's two different chemicals. It's Na, which is metal, and it's NH3, which is a ammonia, right? And then how do you reduce alkyne to a cis-alkene? Remember that? That was early on. It was Lindlar, H2 Lindlar, which was a special catalyst that gives you a cis-alkene. Okay, miscellaneous carboxylic acid reactions. So we'll go from the top and wrap around, I guess. One of the things you learned was the Helvol-Hard-Zielinski reaction, which converts, it's like a three-step process. Remember that? It was, first it made an acid bromide, PBr3, right? PBr3 makes an acid bromide. And then it was Br2, so because that also makes an enol. It's an acid bromide enol. Enols are nucleophilic. The enol attacks Br2 and kicks off a Br, and so you basically you kind of protect the alcohol, and then it makes an enol of the acid bromide, becomes an enol, which is nucleophilic, attacks Br2, that puts the Br there, and then you still have the acid bromide, and then the third step is just hydrolysis of the acid bromide. So water attacks, kicks it off. So we did that full mechanism. That was a pretty substantial three-part mechanism that you learned. And then once you got it, it's like, why would you put a bromine alpha to a carboxylic acid? Well, you can do tons of things like SN2 reactions, and this actually made alanine, the amino acid, right? So NH3 would kick this off and give you the amine, right? What else can you do? We learned, I think we kind of skipped this. Let's not worry about this one. The synthesis of amides directly from carboxylic acids. What we did learn is usually if you want to do this, you would make an acid chloride first. But the book kind of talks about like a direct route, and it's just high temperature and kind of a mess, and nobody really does that, I don't think. And let me see something. And what else do we got? Fischer esterification, totally easy reaction, nice little mechanism. We can also do SN2, synthesis of esters, where base takes proton, makes an O-, and then that attacks an alkyl halide, right? As long as it's a good SN2 substrate, which means it's like primary, secondary usually, right? And then, of course, we can make acid chlorides. That's a cool thing. And once we got acid chlorides, there's a million things we can do, right? We can make anhydride if we want. We can make an ester. We can make amides. Very versatile leaving group. We can make primary amide. So here we made a secondary amide. But we can also make a primary amide. And remember, what can we do with that? Well, that was the, what was this? Something degradation rearrangement. The something rearrangement. Hoffman rearrangement, right? Let me move my picture down. Oops. Okay. Yeah, Hoffman rearrangement. Remember that fun reaction? 2-star reaction. Okay. What about ketones? What are the fun things we can do to ketones? This was all pretty substantial stuff from this course, and we'll start from the top right and go around. All right, so one thing you can do is make amines. That was a pretty easy reaction with amine plus a little bit of acid makes an amine, and then we also learned you can, if you make an amine, you can reduce it. That was the reductive amination. You can also take a ketone and turn it into an enamine, and then we also, as we learned in chapter 18, enamines are nucleophilic, and enamines can you can attach stuff and use this as a way to kind of take a ketone and attach something to a ketone, right? So this kind of shows the contrasting reactivities of a amine and an enamine. Amine is a electrophile, and we can reduce an electrophile with an H-, right? Enamine is a nucleophile. And an enamine we can attack stuff with, and then like and then it makes an iminium. When the nitrogen swings down and attacks something, then you have an iminium intermediate, and that happens to be an electrophile, and then that's how it hydrolyzes back. So you can review all those things. And then of course we can do the Wolff-Kishner reaction, which is hydrazine, NH2NH2, attacks the ketone, and then cool little degradation mechanism that gives us the alkane. We can also take a ketone and make a thioacetal or ketal, and then we can reduce it to an alkane. How do you do it? H2 plus something, rainy nickel. But we could also do this and go backwards, so like deprotect or something back to the ketone. Of course, you can also make acetal. That's a cool mechanism that we always like. Nice one to practice, and that's used as the 1,2-ethane-diol or ethylene glycol, the dialcohol, right? OH, CH2, CH2, OH. Great mechanism. And then there's also the Wittig reaction, which makes alkenes. We learned about that in this chapter. Maybe another one to review. And it was mechanism, probably not an exam-worthy mechanism, but essentially what it is it's like you have a 2-carbon piece. It's called a ylide, a 2-carbon ylide, nucleophilic ylide thing with a phosphorus. Remember the phosphorus ylides? The 2-carbon phosphorus ylide thing attacks the ketone as a nucleophile, and then you had a funny mechanism that falls apart and gives you the alkene, right? That's the Wittig reaction. This we kind of this was actually not. This is not the Helvell-Hard-Zielinski. It's kind of related to the Helvell-Hard-Zielinski, but that was actually a carboxylic acid reaction. Remember the Helvell-Hard-Zielinski reaction was with a carboxylic acid. It made an alpha bromo carboxylic acid. This is a ketone though. So this is just showing that, yeah, you can easily brominate a ketone, because we're talking about ketones right now. Carbonyls, and ketones, aldehydes. So yeah, we can brominate the alpha position of a ketone, and then you could kick that off with a nucleophile. Remember, there's also another thing you can do, which is kick it off in an elimination. This is an SN2 reaction. What if we eliminate it with an E2 reaction? That makes an alkene. And so that's a great way to make alkenes. And why would you do that? Because then you can make an alkene there, and then you can do cuprates, right? Cuprates attack the alkene position. Okay. Amines. Let's talk about amines a bit. Amines. All right. So another functional group we like. Let's start in the box in the middle. Of course, one thing we learned was it was called the Hofmann elimination. So you would methylate it exhaustively. So methylate once, methylate twice, methylate 3 times. So you methylate, and then it actually is a leaving group. The N with 3 methyls is a leaving group, and then with a base, it eliminates, and you get an alkene, and that's a kind of interesting reaction. So it's really methyl iodide or iodomethane, and then excess iodomethane, and then sodium hydroxide, and it just methylates and it eliminates anti-Zaitsev, meaning that the alkene is actually in a less stable position. The alkene goes right there. It's not like the alkene goes there. Why was that? Why did the alkene go one way and not the other? And that was due to sterics, right? This is a huge leaving group, and being a huge leaving group, it's kind of hard to reach that proton. It's maybe a little easier to reach that proton. Okay. All right. What else can we do from an amine? We can make an imine, right? React with, in this case, an aldehyde, and then we could reduce, and the overall process of amine plus aldehyde to imine followed by reduction is also called reductive amination. You could also take the amine and react it with maybe an acid chloride or something, make an amide, then take that and reduce that. So overall, one of the things we can do with amines is convert to other amines, build more complicated amines. It's a functional group interconversion of amines. What are the well-behaved ways of converting alkyl halides to primary amines? Remember these? These are in the amine chapter. One of the things you can do is treat a bromide with like sodium azide, NaN3. That makes a primary azide, and then the primary azide you can reduce. You need a strong reducing agent. I think it's lithium aluminum hydride, LiAlH4, will reduce the azide to the amine NH2. And then you can also do this. It was called the something react Gabriel amine synthesis. Gabriel amine synthesis is the second one. And that one, essentially you just react the bromide with this whole right side piece with the N-, right? Good nucleophile, N-, sodium plus. And then you put that on the arrow, and then that attacks. You get this intermediate, and then it's like just amide hydrolysis like crazy. So you reduce two amide linkages, H3O, heat. You end up getting the amine and this dicarboxylic acid. Okay, both of these are great ways to, and well-behaved ways to convert an alkyl halide to a primary amine. Okay, so this summarizes all of the NAS reactions. This is a big thing in chapter 19 and 20. And so the idea, it's kind of like, you know, what it's kind of showing is how cool the acid chloride is as a, as a versatile intermediate. It can be converted to any of the things on the right, and the reactivity order goes most reactive to least reactive. It can be converted to anything on the right really easily, just using kind of the other side, right? So if I want to make an anhydride, I use sodium carboxylate, or alcohols and amines make the esters and the amides, and then if I want to take the acid chloride and go all the way to a carboxylic acid, it's kind of a boring reaction. But yeah, water does that because this is such a reactive functional group, right? It's a strongly electrophilic thing, and water will totally do that. Anyway, you can kind of see how this is pretty easy to visualize, right? And how as we go from left to right, the reactivity decreases a bit, all the way down to, esters and amides can be converted back to carboxylic acid, and that's and also the ester can be converted to an amide using the amine, and sometimes you have to add a little bit of base or acid to get these to go. But these are called base mediated NAS reactions. And we can also go from right to left. An obvious one is SOCl2, right? Carboxylic acid can go all the way back to the acid chloride. We can also go from carboxylic acid to an ester. That's a Fischer esterification, right? Fischer esterification. And then the this one we kind of skipped because it's a little boring, I think. You can go from a carboxylic acid to an amide with an amine, and then you got to cook this really hot, like 200 degrees Celsius. So that's why it's thermolytic. It's, I'm not a huge fan of thermolytic reactions because they often destroy your molecule because you got to really cook them really hot. Okay. Remember that the Claisen condensation is also an NAS. That was the esters reacting with esters to make beta ketoesters. Okay, these are just kind of cool. So it's sort of a cyclic process. Of course, I can go from a ester to a carboxylic acid and an alcohol using acid or base catalyzed hydrolysis. Good reactions to know. Fischer esterification goes the other way, right? And so that's like H plus. You need a acid. The Fischer esterification, you always need acid catalysis, H plus. It's a very easy mechanism, right? It just snaps the two things together. First you protonate the carboxylic acid, and that's tax, proton transfer, make a good leaving group. Standard mechanism you've seen 1,000 times. Other mechanistically related hydrolysis reactions: nitrile to carboxylic acid, fun one, long, good exam problem because it's like it feels like 20 steps and a lot of potential for little errors, so you got to really pay attention and be careful. Make sure all your formal charges are good and stuff. This one, the Gabriel amine synthesis, second half of the Gabriel amine synthesis, it's another one. It's a long, you use water and maybe catalytic acid, and it's a long mechanism. Okay, so now we're kind of showing the R minus and H minus 1 and 2 equivalent versions of all these different reactions. Okay, so this is acid chloride, and what we're showing here is this kind of cool idea that you can either add two carbon things or one carbon thing, or two H's or one H, depending on which reagent you use, very nicely with an acid chloride. So if you want to add two R groups, you use a Grignard and just do it twice. Well, we say R minus 2 equivalent, but a Grignard is the R minus 2 equivalent reagent for an acid chloride. So two methyls, for example, would tack, you get a tertiary alcohol. If you want to add a single thing to an acid chloride, you can just use a cuprate, like methyl cuprate. That'll add once. If you have an acid chloride and you want to do a double reduction, H minus 2 equivalents, you use lithium aluminum hydride. If you want to do a single H minus addition, then you can use this stuff, lithium aluminum trichert butoxy hydride. This is an obscure H minus reagent, and on a closed book exam, I would say, yeah, just say H minus 1 equivalent, and I understand what it is, and these are silly things to memorize, and I usually don't recommend memorizing silly things. This is definitely a silly thing, but it does something cool. It's an H minus 1 equivalent for an acid chloride. What is the H minus 1 equivalent for things like esters and stuff? It's not this. What is it? It's D and then 5 letters. It's a dibol. Yeah, we'll see that in a second. Okay, for example, esters. With esters, if you want to add two things, it's use a Grignard, and that gives you tertiary alcohol. What if you want to add R minus 1 equivalent, like we did up here with the cuprate? Well, you can't do that. Esters don't do that. There's no R minus 1 equivalent version for esters. What about H minus 2 equivalents? Let's use super reducing agent, lithium aluminum hydride. What if you want to do H minus 1 equivalent? Well, then dibol works, and then it gives you an aldehyde. Okay, and yeah, I guess H minus 1 equivalent is a reasonable abbreviation. Dibol is pretty easy to remember, but on a synthesis problem, if you can't remember dibol, just write H minus 1 equivalent. Okay, amides, R minus 2 equivalents. Is that possible? Well, to my knowledge, it's not. I think I researched this. I didn't see it. Our book doesn't mention it. We didn't mention it. R minus 1 equivalent was also, I think that is possible, but we didn't discuss this in class. But we did learn about H minus 2 equivalents, which was lithium aluminum hydride And that just wipes away the carbonyl. So the carbonyl goes away and you get an amine, right? Remember, you can make an amide and reduce the amide to the amine. But we also learned about dibol, and dibol wipes away the H minus 1 equivalent dibol. In this case, it's kind of like the hydrogen attacks, electrons go up, electrons go down, kicks off the amine, and you get left with an aldehyde. Okay? Yeah. Then we have nitriles. Nitriles are kind of like a similar sort of derivative, and we did learn, well, we never learned about R minus 2 equivalents. I don't think it's possible. We did learn about R minus 1 equivalent, though. Grignards attack nitriles, and you get a temporary amine intermediate, and then you hydrolyze that, and you get a ketone. Okay. We also learned about H minus 2 equivalents. Lithium aluminum hydride just attacks twice. It attacks once, it attacks twice. You're left with a, remember that weird thing? There's a N with a double negative charge. It's like N2 minus. The only time you ever see that, I don't think we really see that very much, but certainly I think in this class the only time you've seen N2 minus is with this reaction, where you're double reducing a nitrile. And then H minus 1 equivalent, and they're using dibol for this. What that does is it attacks once, and then you have a C double bond N, and then that hydrolyzes and you get the aldehyde. Okay? Homologations and degradations, add and lose carbons. Okay, so this just reviews the different cases of homologations and degradations that you learned. 1 carbon homologation and 2 carbon homologations. So one of the ways is just by a nitrile, by its nature, has an extra carbon. So like NaCN, Na plus Cn minus attacks, kicks off. Now you have a nitrile. From a nitrile, of course, you can hydrolyze the nitrile. I'm sorry, this is a reduction. This is, yeah, C triple bond N to C single bond N, right? 3 to 1. 3 bonds to nitrogen, 1 bond to nitrogen. That's a reduction. So that's lithium aluminum hydride. And then hydrolysis of the nitrile is possible. That gives you carboxylic acid. That's a fun mechanism, right? Long, fun mechanism. This is actually kind of a boring mechanism. I don't know why I was so excited about that mechanism. Yeah, what else? Grignards can homologate, homologize, I don't know if there's a word for that. Attach a single carbon, right? Formaldehyde. So that's easy. You can also attach a single carbon through formation of a Grignard and CO2, mixed carboxylic acid. 2 carbon homologation, you know, for the most part, the key one you learned is make a Grignard and then react with a 2 carbon epoxide, and that kind of just adds the 2 carbon piece. That's not that exciting. It's 2 carbon homologation. Also, yeah, compare this with the Gabriel and azide methods, where you like the top one especially, where it's like azide, if you did the same exact thing with the azide, it just does the same exact thing and you get the amine out, but it's not a homologation. It just goes from 3 carbons in to a 3 carbon product. The Gabriel does the same thing also. So both of these convert bromide to amine, but they're not homologations. Degradations, loss, what are we just on? We're in homologations, now we're on degradations. Okay, so loss of carbon, and we saw this one several times. It's the Hoffman degradation. What is the reagents? It's NaOH Br2. Yeah, NaOH Br2. And it's that fun, crazy 2-star mechanism that take off the proton. I'm not going to mention it again, but yeah, that's a good mechanism. And then we got the other degradation reactions. This is the second step of the acetoacetic ester synthesis. This is a degradation with a decarboxylation. So this is simply ester hydrolysis. We might call it the reverse Fischer reaction. It's the opposite of the Fischer esterification. Acid and water, you protonate the ester, water attacks. And then the decarboxylation, yeah, that's a kind of cool reaction, right? Decarboxylate. It's a degradation reaction, loss of carbon. Here's the same thing, but a malonic ester type synthesis. So you have the diethyl malonate derivative with the ring, hydrolyze the esters, and then decarboxylate. Loss of CO2 makes a simple single carboxylic acid. Protecting group chemistry. Let's review what you know about protecting groups. Your initial exposure, which was last semester, was the use of terpbutyl ethers, and this was a great protecting group. Makes a terpbutyl ether with a protection mechanism, and then you would do maybe. Why would you do it? Why would you protect? Well, we have two functional groups, and often when you have two functional groups, you want to work on one and not touch the other, right? And so we protect the alcohol, make it as a terpbutyl ether, and then we what do we do? We now we're ready for our Grignard. In this case, we want to just attach. It's a simple Grignard, right? We have a 3-carbon piece, and we're trying to attach. It looks like benzaldehyde, right? Phenylaldehyde. So yeah, we can turn this into a Grignard, and then we can attach benzaldehyde. So it's 3 plus this extra carbon, and then we deprotect with acid. This is what we learned last semester. Now we've extended this a bit with other protecting groups, and we've learned about the benzyl ether protection, which is kind of recent, right? It's another way to kind of do the same exact thing, but now we make an ether, a benzyl ether. So it's NaH. This is a Williamson ether synthesis, right? It's just NaH is a strong base, takes off the proton, leaves you the O minus. O minus attacks the carbon, kicks off the Br. Yeah, you got an ether now. The cool thing about this ether is it can be removed very gently with H2 palladium instead of H3O, right? And so it's just a different kind of deprotection mechanism. So once you got the protected molecule, we can do our Grignard, and in this case, what is it attacking? What is it attacking? That's a good review question. What are we attacking to get a ketone? What are the things we can attack with a Grignard? We can attack ketones, aldehydes. We can attack ketones. That'll give you an alcohol, so not what we want. We can attack ketones and aldehydes and epoxides and what else? CO2 and nitriles. Remember nitriles? Because nitriles, when you attack them, give you a ketone. Okay. And then we reduce the benzyl ether off to give the alcohol. We learned this one. This is definitely a new organic 2 protecting group, which is a protecting group of carbonyl, a ketone called an acetal. Great fun mechanism. Yeah, you can fill in the Grignard part of this, and the mechanism too might be good to review. Thioacetal had a weird the mechanism of protection is a little weird, and it's not acid based. It uses zinc chloride, right? It's ethane dithiol, zinc chloride, and that's how you put it on. Not a really good mechanism because it's a little weird with the zinc. And then you can oxidize your Grignard, and then once you're done with that, you can oxidize Grignard. What do I mean by oxidize here? In this case, yes, it is an oxidation. In order to do this reaction, you would need to oxidize and do a Grignard, because we're adding, it's a 3-carbon piece right here, yeah, 3-carbon piece. And in order to do this, what you would need to do is oxidize this to an aldehyde, right? Because where's the squiggly line here? Where's the squiggly line? It's right there. There's a squiggly line, right? And so we need to attach phenyl Grignard. In order to do that, what does a phenyl Grignard attack? What do Grignards attack? Ketones, aldehydes, epoxides, and stuff. And so the phenyl Grignard would need to attack an aldehyde, for example, and so then we would oxidize this to an aldehyde. And first you oxidize to an aldehyde, then the Grignard attacks the aldehyde, and then you can either like maybe deprotect with mercury chloride and water back to the ketone, or you can reduce it off. So a couple things you can do to thioacetal. Aromatic chemistry. So there's kind of its own little section, and we just want to review this. It's kind of, yeah, it's its own little world of aromatic chemistry. These are all the simple reactions you learned: chlorination, bromination, nitration, sulfonylation, alkylation, attaching an alkyl group. What's that? Something alkylation. Something alkylation. People's names. Friedel-Crafts alkylation, Friedel-Crafts acylation. All of these, you had benzene and you reacted with a reagent and it made a superelectrophile. Benzene attacked. And these are all EAS reactions, electrophilic aromatic substitution. So distinguish the different kinds of substituents. You should know these. What are the orthopara activators? What are the orthopara deactivators? What are the meta deactivators? The orthopara activators, in this case, there's not that many of them actually. It's really just the alkyl group is an orthopara activator. The other ones that we know of are like OCH3 and OH and things like that. Orthopara deactivators are the halogens, chlorine, bromine. Meta deactivators are all the other ones, nitrous, sulfonic acid. It's all of these things that have a electron withdrawing group kind of off the carbon chain. This just shows, like, we have all these kind of strategies we use, common aromatic strategies, and for example, we can nitrate. It's a meta director, and then we can reduce with H2 palladium or tin chloride, SnCl2, and that gives us a overly active orthopara director, right? Went from meta director to an orthopara director, but this is overly active. So what we did was we made it an amide, and then it's like a less active orthopara director. So now this we can easily attach something at the para position, and yeah, and then hydrolyze off the amide, and then we're left with this. This is one of the strategies you learned. Another strategy we learned is, well, we could keep going and turn it back into a nitro, right? So we can reduce the nitro to an amine, and we can oxidize the amine back to a nitro. It's a specialized oxidizing condition. I don't even remember. It'd be called bracket O bracket. I think it's kind of like MCPBA or like one of those carboxylic acid things. Yeah, and so we learned this in chapter 16, I think, that we can take a ketone. We can either take a ketone and reduce it down to an alkane, so that's H2 palladium, or we can take the alkane and go back to the ketone, and that's, I think, is CrO3, which is weird, right? Because CrO3 usually it takes an alcohol and oxidizes an alcohol. There's no alcohol here. How could it oxidize an alkane? Well, it's because it's a benzyl position. This actually does have some strange reactivity, and CrO3 can actually oxidize this alkane position to a ketone, which is weird. And then this kind of sequence of like nitro is a meta director, and it can be kind of reduced down to an amine, which is an orthopara director that's overly activated, and then that could be protected to the amide, which is just acid chloride, and then that's a less active orthopara director. But the cool thing is these can be shuttled back and forth to kind of do what you're trying to do. Often we'd go from a meta director through this intermediate to the less active orthopara director. Diazonium stuff. This is another little world of aromatic chemistry. So benzene to the amine, and then we can turn it to diazonium species. and it's an aryl diazonium salt. It's a very versatile synthetic intermediate, as you know. And then we have a ton of things we can do. We can convert it to chloride, bromide, iodide. So this is like copper chloride, copper bromide. The iodide is actually the weird one. It's Hi. It's not a copper. It's just Hi. We can do copper cyanide to make the nitrile, and then there's all the fun things we can do in nitriles. We can make ketones, amines, and carboxylic acids. We can also, this is a pretty cool one, because we can actually turn the diazonium into a phenol, because you've not learned any other way to really make these in a general manner. I guess one thing we're not showing is also the azo coupling. Remember that, where you have like another benzene, and then the other benzene attacks the diazonium, and it makes a di. It makes an azo linkage. It's carbon, nitrogen, double bond nitrogen, and then benzene. That's another one. Another cool thing you can do diazonium reactions. You can review that in the notes. This is just a random synthetic strategy where we're, I guess, this is a pretty complicated synthesis. Chlorobenzene. The best way to do this when we're actually, stepping through this is usually you have the starting material and the product kind of right next to each other, and then you kind of go downward and wrap around. But in this case, sulfonation. This is a cool strategy. You're trying to attach something to the ortho position, but you got the para position in the way, so you can block the para position with the sulfonic acid. And in this case, we nitrate, take off the blocking group. You can do that now or later. You can usually just do what you need to do and then take it off. So that was a way to make chloronitrobenzene, and then reduce the nitro, and then diazonium, and then, for example, in this case, a nitrile, copper cyanide, and then nitriles are cool because you make ketones, right? Because ketones, Grignards attack nitriles to make ketones. And then it's like, oh, you have a ketone, and you could add a Grignard or something to the ketone. This just shows kind of like a long sort of synthetic strategy, I guess. And we're applying a couple different strategies. Yeah. A really cool strategy, though, is the blocking of the para position with the sulfonic acid. Here's just another one. This is using the SNAR mechanism, and probably not like an exam-style synthesis problem. Take the bromobenzene. We can dinitrate it. And then this is the SNAR thing. Remember SNAR? This shows, because you have the ortho and para nitro groups are actually, they facilitate SNAR. The bromide it can be a leaving group, so it's cool. We start with a bromine to install the nitros, ortho and para, and then SNAR, which kicks off the leaving group. So then to kick off the BR that we had originally. And SNAR, what does SNAR do? SNAR is just the amine attacks the carbon with the bromine, then pushes electrons through the benzenes, and then it's temporarily stabilized. It has a name. What's that called? The SNAR intermediate. It's called the Meisenheimer intermediate. I think from my memory. And then the electrons go back and kick off the BR. And anyway, and then like in this example, then you reduce the nitros to amines, and then turn those into diazoniums, and maybe make phenols. That's a kind of cool approach from this bromobenzene to this diphenol type thing. There's a lot of ways you can connect these reactions to make complicated molecules. Okay, last little section, reactions with strange mechanisms. You've seen all these reactions before, but it's kind of fun to just put them all in one little section. Reactions with kind of oddball, sort of strange mechanisms. Okay. Of course, the Wolff-Kishner, that was kind of a weird one. The first part's not that weird. It was just making the hydrazone, but the second part's kind of weird. That's like how did that work? It was that NaOH thing where it ripped off the proton, and then it resonated into a carbon negative charge grabs a proton, and do that a couple times and you get the alkane. That was kind of a weird one. The Hoffman rearrangement, you have to agree with me that this is probably one of the weirdest reactions mechanistically that you've learned in the course. Good one to review. That's a little weird. That was one of the later ones, chapter 22, I think. Yeah, the aromatic substitution chapter, where it's like, it was a little weird, right? So I think the idea was the allyl group, this 3-carbon piece, kind of wrapped down, and then the electrons kind of cycled around, and then you transferred the allyl group to the ortho position, and then it made a ketone, and then you have to review that in the notes. This is a little weird, I guess, decarboxylation. So it's like you had acetoacetic ester synthesis, you alkylated, and then ester hydrolysis is not that weird, but then the decarboxylation is kind of weird, loss of CO2. Not even, I mean, it's not that crazy. It's just it changes its, well, it rotates the bond, right? So the OH is poking up, and then the ketone grabs the proton, and you make an enol, and it makes the final ketone. This one was kind of weird. The Beer-Villiger oxidation. Probably not going to be on the exam, but just fun to look at. Maybe review the mechanism for fun. It was a peroxy carboxylic acid. Is like, I think it's like HOO, and then the C double bond O, the CF3, I think. So it's a peroxy carboxylic acid, HOO, C double bond O, and then like CF3. It was a pretty cool mechanism, and it was in chapter 17. Remember, the whole idea of chapter 17 was that you could attach stuff to ketones, right? Ketones are electrophilic. That was the whole summary of chapter 17. Ketones are electrophilic. They like to be attacked by stuff. And so the idea was that peroxy carboxylic acid would protonate the ketone to make it activated, and then the other part would attack, and then it did a couple steps, and then the oxygen got inserted. It's cool. Beer-Villiger. That was it. Wow, we're done. All right, so yeah, hopefully this helps. I mean, kind of just shows pretty much all the cool reactions we learned, and maybe the mechanisms that I think are maybe the more interesting of what you might see on the exam, right? And there's a little bit of redundancy, or how should I say, a little bit of inconsistency. Sometimes I say, oh, this mechanism is so interesting, and then later I'll say, oh, maybe it's not that interesting. Better to just, if you see stars, that's probably a good one. Those are probably good ones to review a bit, and you can ask me some questions in the email. I think exams on Tuesday. We'll have Tuesday office hours if you want to come in and maybe make a list of questions or mechanisms you might want to talk about, and don't just say like, oh, just show me all the mechanisms. Yeah, I mean, a lot of this you guys know now, right? Yeah, maybe a couple things need review, and also we have all the recent video lectures which explain everything pretty in detail. I think the other thing is I'm going to give you some multiple choice practice problems, because there will be a little bit of a multiple choice component on this exam, so that should be posted today at some point Friday. All right, see you guys. Bye.